repeat too much, especially since I'm going into the detailed discussion on the same day that I gave the overview. But I do want to try and flesh out a lot of what I already covered, provide a whole bunch more detail, hopefully provide a little bit more information about uses, limitations, where we can go with this, and particularly how the climate modeling, the permafrost modeling, the fire modeling are going to connect to some of the talks that you're hearing later, that interconnectedness, that trying to draw some conclusions, answer some management questions, address the core analysis. So I kind of got that in the back of my mind as I talked through this. As an introduction, I think most of you already know that there's pretty good evidence that the climate is already changing. So when we talk about projecting future climate change and change from current to future, we're already dealing with a moving target, and that, not to belabor it, but it does make for some interesting challenges where, for example, if you're saying what species, what vegetation is currently on the landscape, we don't always know whether that is what's there is there because of the climate the way it is now, or because of the climate the way it was 10 years ago, or 20 years ago, or 50 years ago. And it might be all of those answers depending on the species or the system. So we're already dealing with something that's kind of an amalgamation of change, and that's something to keep in mind as we're trying to think about lag times and think about how that changes into the future, is that we already are a little bit uncertain about how much change is already underway, like the ball's already rolling downhill and we're chasing after it. But yes, there's a lot of evidence already that climate is already changing, permafrost is already thawing, hydrology is already shifting, and that goes along with changing landforms and thawing, slumping, all the visible changes having to do with altered soil thermal dynamics, and then changing biological processes, which includes everything from the species level up to the whole ecosystem level. And then the other thing that I've said before, but it has to always be kept in mind, is that all of these pieces are connected, and often we have to address them singly, and you're hearing different people speak, talking about invasive species and talking about swans and so on. But we've been doing our very best when possible to show what those linkages are or may be, and we've also done our best to show where the data gaps are, where we know that there's some linkage. We know that A affects B and B affects C, but we don't have the literature, we don't have the data to be able to meaningfully say what that linkage is or how it functions. Sometimes just knowing that the linkage is there can help inform decisions, though. And so, ultimately, we want to be as open as we can about, what is likely, what is probable, and where the decisions lie, for managers. What questions can be answered, what questions can be hinted at, and what that means for future choices. I just put that little box in there again. A lot of the data for the climate modeling came from the Scenarios Network for Alaska and Arctic Planning. I won't really tell you anything about methods because you've mostly heard it before, and because you can either ask me privately or dig through our website as to where a lot of those models came from. But do interrupt me if something I'm saying about climate modeling is completely obscure or confusing because I haven't gone over that. Interrupt me and ask me to explain it. So early this morning, we had a couple of really good questions about either model sensitivity or model uncertainty, which are not exactly the same thing but are related. And we struggled hard with this as a group. The fact that very little that we can say is going to ever be 100% certain. And to insert an anecdote, I've got two second graders. They just finished second grade, and for some reason they had this whole set of homework where they were being asked to qualify things as being either impossible, unlikely, likely, or certain. I guess getting the idea of, beginning of scientific inquiry, or, what should you believe? I kind of like this because it was like, let's sort out reality from, but the thing that was really really amusing to me is that one of my twins refused to ever say anything with certain on this homework assignment. So, the question would say, like, you will get out of bed tomorrow morning, and she put, likely. I was like, why did you select likely for that? She said, I could be really sick tomorrow. And then one of them was like, the sun will rise again. And she put, likely. And I was like, Molly, where are you going with this? The sun might explode. And I thought of that this morning when I was thinking about our struggle with certainty, because we often can't put numbers on it. And even when Nancy, the scientist, puts numbers, plus or minus 5% p-value of this, there's still the sense that, there's wiggle room. You've tested something, but maybe there's another source of uncertainty. Maybe you've managed to put boundaries on this source of uncertainty, but there's another source of uncertainty not accounted for. And I do a lot of work with scenarios modeling, and what it comes down to is the question of how certain are you in relation to your choices and your behavior. Like, yeah, my kid's going to get out of bed tomorrow morning and the sun will rise. It's not certain, but it's certain enough that the uncertainty doesn't affect my life. And then there are other things that are in that middle ground where it's probable, but you still have to hedge your bets that it might not happen. Or it's extremely likely, but you still have to deal with the fact that it might not happen. Or it's only slightly likely, but if it does happen, it's so catastrophic that you might want to put a lot of resources into contingency planning. And that's something that I think we all instinctively do in our daily lives. Like, the possibility of your house burning down isn't that high, but you get fire insurance and so on. And I try to use that mindset when I'm dealing with multiple uncertainties. And I know it's frustrating, and it frustrates me sometimes because I like numbers. My background is in science. I like to be able to say plus or minus 5%. But the truth is that, as I said earlier today in the discussion, any time that we can even narrow down, if you imagine possibility as being a full circle or globe extending in every direction around you, and if you can narrow that down to a pie wedge, then you've done a huge amount in terms of directing resources and directing possibilities. So that's just my little take on before I start talking about uncertainty. That all being said, we really were struggling to come up with a metric by which we could talk about uncertainty in climate modeling, because these climate models link to a lot of other things. They link to the permafrost model and the fire model, but then they link to the conservation element and to a lot of the other pieces of the puzzle. We said, well, we really need to have some idea of what is meaningful change. We won't say significant because that has the scientific, baggage attached to it. But what is meaningful? For what kind of change should you change your management? For what kind of change should you say, we're not changing management yet? So what we did is we looked at the variability amongst the 5 global circulation models that we use in creating our average, our compiled 5 model outputs, and took a standard deviation of the output, across the outputs of those models, across all the pixels, across the REA maps, for temperature and for precipitation, and said, okay, month by month, these are some of the standard deviations in projected monthly temperature. And so you sort of get this rough picture averaging all across it, which is not the be-all and end-all. You come down to this number in the lower right that says 1.2 degrees Celsius. That doesn't mean that if the projected change is less than that, then it's absolutely meaningless, and if it's more than that, that you should change all your plans. But it gives some sense of the order of magnitude of what is meaningful or less meaningful change. And again, I'll point out that some of this you can say is uncertainty in the sense of these models might be wrong, as in, not parameterized correctly, but actually a great deal of that difference between models is not so much wrongness as natural variability. All the models are built such that if you look at the ups and downs month to month and year to year, they look a lot like real weather data, which is wonderful. It means the models are good, that they've got these, and we've done, if anyone's interested, on the SNAP website, we did a sensitivity analysis models mimicked those ups and downs, whether they mimicked the trends, and the models performed pretty well in that. But that just gives you an idea that there's this built-in variability in the models. We're dealing with that in the same way that we deal with real variability in climate. Okay, so that's my spiel on sensitivity and uncertainty. Then just a little bit of background on scale of analysis, and you've already seen some tables in which there were these categories of, the lower Yukon, the upper Kuskokwim. We chose to do some of our analyses, or to present some of our results, I should say, at this level. All of our analyses were actually done at the fine scale as dictated by the RA guidelines. But for ease of showing people graphs, showing people maps, showing people tables, these are categories that are larger watersheds. They're called the third level packs. Big watersheds kind of give a regional basis for some of the outputs. So you'll see some of these place names in some of the tables, and that just gives you an idea of where they are. A lot of our outputs are in map form, and I tried to spare you in this presentation. I took out the slide that had 18 maps on it, let's put it that way. We went through these yesterday, and I was told kindly that maybe that one wasn't so good. But I'm keeping a few in here because these are actually at the core. Management question 20 is kind of a run-on sentence that asks, how will temperature and precipitation and season length and basically everything about climate change over time, and how do model outputs differ for the A2 model, which is the one we focused on, versus the A1B, which was another option that we could have focused on. So big, long run-on sentence. A lot of the outputs we produced address that one management question because it's really a bunch of questions rolled into one. The takeaway from this 8-map slide is that both the A2 shown at the larger size, that's the A2 emission scenario is the one we ended up focusing on. The A1B we set aside. The rationale for choosing one scenario rather than continuing to look at two is, first of all, over the time period we're looking at, the two are remarkably similar. The A2 is a more extreme emission scenario, but the way it's written, the future world that it describes in terms of human behavior is one where most of the bad juju happens at the end of the century. It sort of accelerates upward like this. So in the time frame we're looking at, there's not much difference between the two. Emission scenarios are just that. They're scenarios. They're hypotheses about how global development might pan out and which nation is going to gain more wealth and more resources when. So that's another source of uncertainty, but I think in the time frame we're looking at, it's actually not a very great source of uncertainty. What you can see from both sets of maps, the A2 and the A1B, is that there is distinct warming in winter temperature. I think it's actually shown better in table form, which you've already seen a table of January temperature. But you can see that, essentially the color is moving northward. So, what was the temperature down in McGrath, moves up to be the temperature in Galena and so on. A distinct warming trend that continues across the time period. For winter months, it's already a distinct trend in even in the near term. For the summer months and also for those shoulder seasons, as a couple of people have already said, and I'll go on to summer temperature here, the trend really is not super visible. Those first two maps, if you look at them, the 2010s and the 2020s, they kind of look like I did a copy and paste. They look really similar. So we're not seeing as much immediate trending in the summer temperature or in those freeze-thaw days, shoulder seasons, until later on, and that has maybe some ramifications when we start connecting with the CEs.
Nancy, this is Cindy. Can I just ask really quickly what the pixel resolution is on this map that we're looking at right now?
The pixels in terms of the data analysis is 771 meters. The actual pixels of what I cut and pasted.
Are these 30 by? Oh no, I mean are these maps 30 by 30s or 100 by 100 meter pixels, or what's the pixel size?
They're the pixels. It's 771 meter resolution. So the GIS files that were used to create these maps are at 771 meter resolution.
So each pixel is 771 meters by 771 meters.
Yes.
Okay, thank you.
Yeah.
I was just curious why, if you have an idea of why there would be more intermodal variability in January temperatures than in July, just looking at your.
Probably because there's more trending change in January. And so, yeah, there might just be more disagreement for that reason. There's kind of more room for disagreement because there's more change being projected. And it also could be randomness within the randomness, if that makes a certain amount of sense, you know.
Yeah.
Where two different models both happen to predict particularly cold Januaries in the same year. So it's, yeah, it's like the second derivative of uncertainty and the third derivative of uncertainty. Okay, and so again, this is another table similar to the one you saw for temperature. Same thing, trying to get at some metric of uncertainty for precipitation so that we have at least an order of magnitude grasp on what is meaningful change in rainfall or rainfall equivalent, which is what these numbers are in millimeters, or versus what's just spurious noise. And it does bring out a key point, which I think someone kind of mentioned earlier today, is that precipitation is notoriously all over the place in terms of what we all experience in daily life. Like it's raining on one side of the hill and it's not raining on the other side of the hill, and weather forecasters are pretty bad at guessing timing and number of millimeters of rainfall, and it varies spatially and temporally a lot more than temperature does, which means that in modeled precipitation there's also more variability, which is as it should be, because if the model came back and said that it was going to rain 2 millimeters every day for all 365 days of the year, that might add up to a realistic amount of precipitation, but it would be a terrible model if what you care about is mimicking reality. So again, we kind of tossed all 5 models together and looked at the standard deviations, and you can see there, even the standard deviations vary. In this case, the numbers are higher in the summer. There's more uncertainty in the summer than in the winter. The big average of all the averages comes out to 7.5 millimeters. So again, that's just a really broad metric for saying that if the trend that you see is less than 7.5 millimeters, it's probably not really a trend, or it's not enough of a trend to hang your hat on in any way, just to give you some idea of scale there. And again, we did that same comparison. It was part of the management question, comparing between the A2 and the A1B. And again, you can see that there's not a huge difference between the A2 and the A1B, which was nice for us to discover that, because it meant we didn't really have to agonize over which emission scenario we were using. SNAP does have a third emission scenario, the B2, but that one, the literature tells us, in fact, that the A2 is probably the closest to the real trajectory that we're on in terms of what the population is doing. The A1 still sort of, potential. The B2 is, can you please stop typing in mute?
Somebody's off mute again. If you check.
Thank you.
So you don't need to be.
The B2 is just way too optimistic. These scenarios were created a few years back, and we've already kind of turned our backs on the B2. So from among the scenarios we had to choose from, these were the most realistic, and the A2 is probably the most realistic, and it turned out to give these results not that different from the A1B. Again, you can see the scenario over time is showing an increase in precipitation, but it's not a dramatic increase. In the report and all the other outputs, you can see this in tabular form as well as map form. It's a little easier to read and graph. Again, this is all at 771 meter resolution, so it can be spatially analyzed at that scale. But just looking at the map doesn't immediately leap out at you as what sort of the take home is from that. Like, okay, there's a little bit more, more precipitation occurring, but again, how does that link to anything? And we're going to talk about that more during my talk, but also especially during all the connected talks when we talk about how CEs are affected. Oh, here you go. I did throw in the completely blinding table. This is like the worst PowerPoint slide ever. This I should have at least highlighted the right-hand row there. from the change from the 2010s. So you can see, what are the, how many millimeters have increased from the 2010s to the 2020s, from the 2010s to the 2050s, and then the same thing expressed as a percentage. What this shows you is that there's a definite trend toward more precipitation, that it's not far outside of our standard deviation, but it's a couple of standard deviations. So it's a meaningful trend, but that still doesn't actually tell you about what it might mean on the landscape. We broke down precipitation into summer, winter, and annual precipitation to try and get a handle on different variables, different questions that can be answered with those different pieces of the data. And the key take-home about winter precipitation is that it's a little bit of a trick question, because every model tells us that winter precipitation is increasing, in the sense that the number of millimeters of rainwater equivalent in December, January, and February, you add it up and say, oh yeah, it's going to be more. But if some portion of that is falling as rain instead of snow, then you might actually be getting less snowfall, and most people think of snowfall as winter precipitation. And what's happening in the shoulder seasons is going to have a big impact. And then you get the same trick question going on in summer. Yes, summer precipitation is projected to increase, meaningful increase in precipitation, but you've got this fairly large increase in temperature, especially in the long term, not so much in the near term, and that means more evaporation and more transpiration. So the question of whether it's a net wetting or drying impact, and in fact, some years back, SNAP created a PET model, a potential evapotranspiration model, and we did all this mapping statewide. We didn't include the outputs from that model here, in part because they're so ambiguous. They tended to sort of say, well, it looks like it might be a little bit of a wash between slightly higher precipitation, higher evapotranspiration. We don't really know whether it's getting wetter or drier on that score. As I said before, the key player might end up being the permafrost thaw rather than actually the precipitation. But we really did care about the snowpack. So, maybe summers are going to be neither wetter or drier. It's a little unclear in terms of water availability for plant growth. But in terms of snowpack, there are a lot of questions, a lot of species. It really matters when the snowpack appears, when the snowpack disappears, how deep the snowpack is, how compressed it is, how much rainwater is in it. Unfortunately, this is a data gap. There are not good data sets for this, and we've talked to so many different people trying to find better data sets. Part of the problem is it's just a really complex algorithm, because it depends where the snow blows to and how much it warms during the day and how much the snow compacts. The one data set that we did manage to create is snow day fraction. And so they're pretty good algorithms for calculating snow day fraction. I just threw up some sample maps. We actually have this for all of the non-summer months, for all the time periods. I threw up as examples current January and distant future January 2060s, and then same for October. Kind of pointing to the fact that what we're trying to get at is a couple of different things regarding snow day fraction. One is, in the dead of winter, in January, is all your precipitation falling as snow, or are you getting some rain on snow events? Because those rain on snow events are really key single events that can hammer caribou and other species. And then the second, related but very different question is, what's happening in the shoulder seasons? Is the snowpack coming later and leaving earlier? So we look, like October, April, what's going on there. And you can really see on those bottom maps a pretty big shift in the expected percentage of October precipitation that would be expected to fall as rain versus snow. So it tells you something about when the snowpack is appearing and what's happening in those shoulder seasons. Okay, so then the next variable, again, it still says management question 20, because I'm like sort of remedial here. I'm still working on one management question. We have a relatively simple model for day of freeze and day of thaw, and I always have to stop and define what that is. It is not the day on which, like, the pond outside your house freezes, or it's not the day when the ice goes out on, and the tripod goes out on the in Nenana. It's just simply the day when the running mean temperature crosses the freezing point. So there are going to be lags between actual thaw, actual freeze, and when the running mean. But it's a really good measure. It's a really good comparative measure in the sense that if we cross that running mean on whatever April 15th now, and then it's going to be 5 days earlier, it's projected to be 5 days earlier. That gives you a really good idea of how the shoulder season might be shifting. And these maps, here you have the whole state, and you have the REA outlined, and it gives you just a sense of sort of how that fits into the picture statewide in terms of where the data freezes and where the data thaw is. And you can see a pretty big shift. I put this actually into a graph because it's a little easier to see, and it has a table below it with the actual date. So for those different regions, for example, if you look at the the Port Huyton area, that one's got a pretty radical shift for the day of thaw here. I shifted from talking about day of freeze to day of thaw. It's the same thing, but in the spring, where the current and near future both say 11th of April, but then you see a shift pretty radically to the 5th of April and then the 1st of April by the 2060s. So that's 10 days earlier thaw predicted for that particular region. And from that, there are all kinds of potential human ramifications and ecosystem ramifications. So here's a really long laundry list of limitations and data gaps for climate. Some of these I've already touched upon this morning, but obviously the uncertainty, the stochasticity means you can't be that precise with predictions. You can artificially put in a whole bunch of decimal places, but it's misleading to do so. So you have to get a sense of the trends and what's meaningful and what's not. And the climate data are at monthly rather than daily resolution. I already talked about that. Makes it a little harder to get a hold on those extreme events. And the temperature data, they're not for water temperature. Precipitation data don't differentiate between rain and snow. We try and get at that with the snow fraction. And the sparse climate stations, we talked about that this morning as well. I just mentioned that the data used for day of freeze, day of thaw, and season lapse are interpolations. So they're linear interpolations between the monthly data to figure out a likely crossing point of the 0 Celsius mark. And that they're not directly correlated with measured ice out. Although the data, because of people gambling on when ice goes out, there's some great data on that, and it does show that ice has been going out, at a statistically significant level, has been going out earlier over the course of 100 years. There's actually data from Yukon territories as well that matches pretty well to what we have here. And I'll repeat it again that we have this great climate data, great projections. Unfortunately, there's sometimes a disconnect in the literature between, we know a species is affected by climate. We know the climate is changing, but the variables haven't been mapped or just don't match up. So we struggle. We have lots of back and forth conversations. Well, can you find a study, an article that that links June temperature or January temperature or any month of temperature, okay, we can deal with it being summer temperature, we can average across months, but they're often, the variables don't play well together, and so you can't always find what those thresholds are. And the same thing with the scale and the details. So creating those attributes and indicators tables is a struggle. Okay, I'm going to stop. I separated out this discussion of Cliomes, which are the climate clusters, climate biomes. They're part of climate, and yet they're not. So I'm going to stop here and see if there are any questions. Have I lost anyone before I jump into this, because this part's confusing?
Nancy, this is Paxton from Anchorage Field Office. Earlier, snowpack was mentioned, I think, by Tracy about not good enough or snow depth data.
Yeah.
And do you consider that part of climate or like a separate category?
I think it's part of climate, and I just touched upon it a bit in saying that it's a data gap that we would love to help to fill. I think that one of the variables that would help define, well, two of the variables that would help define it are temperature and precipitation, but the algorithm that would help create a really good snowpack model would also include information about wind and then a lot of like almost just the physics of snow behavior. It would have to be daily climate data rather than monthly. So we have a long-term view toward creating that model, but it's not something that's near completion. It's still a data gap right now.
Aren't the climate stations kind of preferentially chosen in lower elevation areas?
Right, we have, they're like, no, people don't put long-term climate stations on top of mountains or, so the data are skewed, which is another problem. The data are skewed because climate stations are not randomly located, obviously.
Well, you said there wasn't suitable snow depth layer, so that means there is snow depth data available, and who's it available from, the NOAA?
Well, they're like sporadic data sets from like particular locations. The problem is people have gone out and tried to ground truth, they've gone out and measured, and snow depth varies on a really fine scale as well. That's part of the problem, that if you go around like with your measuring pole, and like your snow will be like 3 meters deep, and then 20 meters away it's completely blown clear. So that's another problem with snow depth layers, is that people have created them on a really localized basis, and I could try and track down some of those, but there's nothing even approaching a statewide layer, and if there were, I'm not sure how we would deal with those issues of microscale. It's a thorny problem, and those microscales really matter. Obviously, if what you care about is caribou being able to dig down and get to some lichens, it doesn't matter if those 3 meters deep in some spots, so long as like a few meters away they have bare spots they can get to. So, like the operational scale issue is a real problem for a lot of the questions we want to answer.
So this is an example where 1 kilometer or even 100-meter data would not, like from satellite, generated from satellite imagery would not be sufficient then.
It might not be, depending on what you wanted to know. But the example that I gave, of like whether caribou can dig down and get to the lichen, it might not be sufficient even at that fine a scale, unfortunately. Yeah.
Thank you.
Oh, thanks. Were there any other questions before I continue on and talk about climate clusters a little bit? Okay, so this is really part of the climate discussion, and I should reiterate, if you're confused by these being called Cliomes and being given this invented word as a name, all it is a climate cluster. All it is a way of looking at the 24 climate variables that I've already presented as one variable. So I've been talking about 12 months worth of temperature and 12 months worth of precipitation data, and all of those, they vary in parallel. Obviously, it's like it gets warmer in the summer and it gets warmer in the winter as climate warms, and precipitation is projected to increase across all months. But the change in each month isn't the same as the change in another month, and being able to roll all 24 variables into sort of one uber variable in some ways makes it easier to take a pixel on the landscape and say, how much is this pixel changing with climate as compared to this other pixel over here? So it lets you, sort of assign some values to the amount of change, and it also allows you to assign a climate category to a pixel. So that's what climate clusters are, is they're just artificially machine-generated categories where like is grouped with like, where you say, okay, and in the case of this project, which SNAP did a few years back, we took the whole landscape of all Alaska and most of Western Canada and turned it into 18 of these clusters, where within each cluster it's as similar as it can possibly be. And then, obviously there's some blurring at the boundaries because the clusters blur into each other. But what we were trying to get at is this question of, if you have kind of a known existing climate in a particular region, where is the climate associated with that region likely to shift to, and what other known climate-associated cluster is likely to shift into where you are. And it's a very holistic way of looking at linkages between climate and the landscape. So that being said, the graphs that you're looking at right now are the clusters. Out of those 18 clusters that we created for this previous project, these are the clusters that occur within this REA. So they happen to be numbered 8, 10, 12, 14, and 15. That's arbitrary. But these are the clusters that we found within this region. And these are how they're defined. So you can see, like, cluster 15 is the coldest one. It has typical January temperatures of like about 23 below 0 Celsius, and typical summer temperatures of less than 10 Celsius, and so on. And then the bottom profile is the same clusters for precipitation. So you can see that cluster 14, the salmon-colored one, is a lot wetter across all months, but particularly really wet in the winter months. So cluster 14 is characterized by having a lot of snowfall, but it's also one of the warmer clusters, so, you know, maybe some of that snowfall comes as rain. So it just gives you this idea, and we wrote up in the full report for this project lengthy descriptions of what the climate is like in these clusters. And this is what the same clusters with the same color scheme, same colors from the graphs, are here on these truncated statewide maps with the REA outline in dark black. So you can see the projections for how those climate clusters might shift over time. Obviously, you see, not surprisingly, you know, clusters which are currently in warmer areas spreading northward, and some of the clusters that were pretty dominant, that green that's pretty dominant now and in the near future, all but disappearing. And that's a climate pattern that's currently quite characteristic of the interior. You see a bunch of that color around Fairbanks. You see it in the northern part of this REA. So that, you know, for anyone who lives in this region or works in this region, that would be what you think of as normal weather, normal climate. That's kind of status quo across temperature, across precipitation. You know, and what's replacing it in the model is more characteristic of more of the southern boreal. But I should caution to say that we're pretty confident about these shifts in terms of climate. It's really thorny when you start trying to extrapolate anything from this about vegetation or species or land cover for a lot of reasons. I mean, the obvious one is that there would be some lag time. What you can say is that a species that's currently got one characteristic climate is projected to have a really different characteristic climate in another 50 years. Maybe the species aren't going to all shift there, but they may be stressed. You know, so maybe some species will shift, others won't. There'll be certainly some species that can seed and move much more rapidly than others. So it's certainly food for thought in terms of the perspective you have on climate change. We
Nancy,
did try to, yes, sorry.
I know you said you weren't going to get too much into methodology here because of time, but I'm just trying to wrap my head around it. Are these geographic clusters? Are they some sort of statistical clusters like principal components? Or?
They're statistical clusters that were created by partitioning around medoids. So if you imagine, I can't think in 24-dimensional space, but a computer can.
Right.
So if you say this point in space is defined by 24 variables, like January temperature, February temperature, 12 temperature variables and 12 precipitation variables, and you tell the computer to define that point in that spot in 24-dimensional space, and then you tell the computer to group together all the closest points in that 24-dimensional space. This is what it creates. It's hard to wrap your head around, but it's a statistical model. So so that kind of ties in actually to what I'm showing you now, which is how well do these climate patterns match anything that you actually see on the ground? And the answer is they don't play together all that well when you compare them to the land cover mapping that Jamie talked about earlier, and we'll talk about again. That's not actually that surprising when you realize that, you know, if you go back really briefly, you realize that the areas that are depicted here as different colors, different clusters, aren't necessarily areas that have completely disparate vegetation. They might have somewhat disparate climates, but they don't have like entirely different species between the part that looks in the current map, light green, and the part that looks salmon color. They do have different climates, and they do have different proportions of those different land cover types. So what we played around with a little bit, and some of it turned out to be kind of interesting, is looking at all those clusters that occurred in the REA and seeing what proportions of the different land covers they matched up with, and then thinking about if you were to imagine that those proportions held true in the future, what would that mean for shifts in our land cover types? This is pretty hypothetical, because again, the land cover linkages are proportional rather than absolute, and it's assuming that those percentages would stay the same and so on. So I wouldn't use this as a predictive model, but I think it is really pretty interesting in terms of thinking about which portions of the current land cover and which areas within the REA might become more or less stressed as they are no longer in their current climate envelope or typical climate region. And we played around with it a little bit more, where we said, okay, what about which of these areas, which of these land cover types are good habitat for caribou, poor habitat for caribou, and so on. And again, if we assumed that the percentages held true as the climate shifted and that the land cover types remained linked to those climate envelopes in this hypothetical future, these are some of the changes you would see. I think some of these might be more realistic than others. There's what this tinkering with the model does is it tends to show an increase in shrubby vegetation, which is why you're seeing improvements for moose habitat. It shows improvements for caribou habitat. I think those are more spurious because this climate clustering is not linked to fire. And so when I get on in a moment to talking about fire, the increases in fire cycles would most likely take out a lot of the lichen that the caribou are looking for. And so any slight improvements that might occur due to these sort of shifting percentages of vegetation would be likely negated by that. It's really this is pretty hypothetical and pretty complicated, and I encourage people to ask questions now, but also to dig into some of the language in the report, and even to go to the original project report from the Cliomes project to sort of see how we try to interpret some of the Cliomes concepts. But data gaps for this section. Obviously, vegetation categories are broad and encompass many species, and we can't really swear by a linkage between climate clusters and precise percentages of the different vegetation types that occur in there, just because there are other variables at play in terms of how those percentages would play out, and because there are time lags. We're already, as I said at the beginning, we're already in a system that is stressed because it's already on a climate change trajectory. So just because there's a dominant cover type within a particular region now doesn't mean that dominant cover type is 100% best suited to the climate that's there right now, because it's already being pushed. And this idea of the moving climate clusters just means that the pushing will continue. And as I just said, the fire may be kind of the wild card in this, because you can look at kind of the slow change that's driven by climate, but the threshold change of a fire coming through resets things and can make much more rapid shifts. Again, this is confusing, and I know it is, but I'll take some questions now so I can.
Could you go back to the map?
Yeah, that one. Yes.
Some of the things I think that are interesting about this geographic area, especially on the west side, is the theoretical rapidness of the Cliomes change. In several areas, especially on the west side, it's changing, like in that upper corner from this light blue color to green and then to navy and some salmon. And then further down, it's going from green to navy to salmon or light blue. I mean, there's a lot of turnover. It's not, in the southern part, it's kind of, the salmon is expanding. So there's kind of a one-color change, but in some areas there's multiple changes. And I guess a time lag issue, but it does mean that, when fire comes through in this area and there's some predicted fire increase, right?
Yeah.
That we're going to have forcing events that could have some weird things going on.
Yeah, and, it's interesting, part of the reason that we presented this as more of a, not quite statewide, but as a larger map with the REA outlined rather than clipping the REA, is it gives you a sense of how climate clusters work better in some regions than others. If you look at the Arctic, it's a much kind of clearer story, like the pink area is just getting smaller and getting squinched up, and those coastal red areas go from being like dominant all across the coast to being just little outposts of red, and that makes a little more logical sense when you think of warming in the Arctic, and some interior species creeping up into the Brooks Range, and that and you can see the Alaska Range sort of sticks out as being a separate cluster at high elevation. So anyone who's familiar with Alaska can sort of mentally ground truth this a little bit and say, yeah, okay, I can see where climate forcing would do that. The region that happens to be the region we're most interested in is actually one of the areas that proved to be most thorny for us when we did this as a statewide analysis. And I think part of the reason for that is that I was describing the way that this clustering model works, and it finds the best fit. You say, okay, you've created a 24-dimensional model, and then you give the model the future climate data and say, just match each pixel to what's the best fit, and it has to basically interpolate all those 24 variables and find what fits best. And if there's nothing that fits terribly well, it still has to pick the best fit. And I think to some degree that might be happening in some of this area, because, for example, one of these colors, this chocolate brown, that granted only comes in a little tiny splotch and probably isn't really meaningful, but that chocolate brown comes from southern Saskatchewan. That was the best fit. I mean, that's like canola farms, but it was the closest fit to the projected future climate for a little piece of the REA. And I think that actually is itself a pretty interesting story, is that the new pattern of 12 months of precipitation, 12 months of temperature, the pattern of climate in some parts of Alaska and some parts of this REA is actually unique. It doesn't fit terribly well maybe with any of these 18 clusters across all of this area, which is actually kind of mind-blowing, because this is a lot of ground. That's a lot of different climates, a lot of different clusters. And you can see it patterns really nicely across the Midwest, where everything's all flat, and it's just like you go north, it gets colder, you go north, it gets colder. But this is a complicated area, and there's not necessarily a pattern that fits that well, and that in itself, to me, speaks of some potentially stressed out systems, because the only species that you can have coming in and being dominant are really the ones that are either invasive or the ones that are close enough to be moving in and feeding in, and it means there's some uncertainty there, but there's also a pretty interesting puzzle as to how that will pan out.
I guess, in this case, it's not really going to help us very much necessarily in our planning, but it might help us a lot in figuring out what our monitoring scheme might want to be.
Yeah. Yeah.
So that we can start to get a sense of what is really maybe going on over time.
And it'll be very interesting to kind of tag back to this, to see whether some of these changes do turn out to be vegetation or biome changes, to see if some of the areas that are projected to sort of shift and they can't figure out what they are, what species do crop up new or turn up as invasives in those spots. What we did when we did this as a statewide project is we actually tagged those areas that, as you noted, areas that kept switching back and forth. We tagged those as areas of potential vulnerability, and we tagged areas that didn't change at all as areas of potential resilience. And that, I think, is an interesting way to look at it, too. That an area of vulnerability doesn't mean that everything's going to go to hell in a handbasket in that spot, but it means it might be an interesting region to monitor to see what vegetation change might occur there.
And since Kent's here, I'd say this might imply that it'd be a really interesting place to do post-fire monitoring. Because when that forcing event happens, really interesting things could happen on the other side.
Yeah, when something burns and then you don't have any idea what's gonna come
Right.
back in its place, yeah. Yeah, that would be, monitoring those sites would be wonderful, and that kind of fills in some of those data gaps. That's the kind of project we would love to see happen. And I will now charge ahead into fire.
30 minutes.
I know.
Yeah, okay.
I've got 30 minutes to do fire and permafrost, but these are shorter topics, and I've covered them quite a bit already. And I'm finally not talking about management question 20. I like completely graduated to 22 here, which was basically asking what fire history of the region is. So this is nice because the data exists, but there's this data gap that I mentioned, which is that there's great information about where things burn, but there's not really information about how severe, how deep, how scarring, species replacing these fires were.
Nancy, is there an effort to do bark maps or burn-severity maps from now on?
Yeah,
forward?
all the current fires are, first of all, they're maps. I mean, these were like drawn on the outline, the outlines are like sketched on, so often they're like areas within what's marked as a burn that didn't burn at all, and so there's that. Now it's all like, from space, and it's like completely pixel by pixel, and now severity is being mapped a lot better as well, and often severity can also be, mapped from space. Actually, the Geographic Information Network collapsed into a lot of that work, at UAS, and I could probably get you data because I have some of the program there.
How about in the Arctic areas for the fire perimeters? Were they even recorded prior to like 10 or 20 years ago?
Tundra fires?
Yeah.
Yeah, there are.
I know there are a few polygons up there, but does that mean somebody happened to be there and drew it, or?
Yeah, they're pretty patchy. They're the polygons. There are polygons going way back, but I think there were most people think there were a lot that were missed, because, grass fires are just not as extreme, and there weren't people up there mapping them. So that's part of the problem with there's underreporting in tundra fires, which completely throws off model calibration.
Yeah.
That's a problem. So obviously this map shows you obviously a lot less fire history towards the south, and it also, if you delve into it, shows that an increase in fire over time. And again, this picture really shows how stochastic fire is, because if you happen to be right in the middle of this orange fire, it's like there's some really huge fires, and there's some huge fire years in here, and then there are periods of time when not much burned, and so again, it's fire is spatial, but it's can't predict it that spatially. And then this is the same map that or set of maps, I should say, that I showed this morning, with essentially the same message that what we were able to do was run Fresco. Yeah, I'll give you a little bit more detail here. The Fresco fire model, as I've already said, is a spatially explicit model. It runs pixel by pixel. Each pixel has encoded information about what species is growing there, what the age of that species is, and then what the weather conditions are, so temperature and precipitation. And this all goes into a big algorithm as to whether, when the fire comes to the pixel next door, does the fire spread into your pixel or not spread into your pixel? So if you have like a pixel that burned 2 years ago and now it has fireweed, probably doesn't spread. If you have a pixel that's all ice or snow, probably doesn't spread. So it's all probabilistic. And we were only able to do this for the forested areas. That southernmost Huck 3 is the one that's much less forested. That's only 51% forested. All the rest of them are like at least 85, I think. They're all in the 80s and 90s, up to 97% forested. And again, take-home message is that shortened fire cycles, increased burning, projected all the way across the map, but with some very clear leveling off by mid-century, primarily because the models go up, and then because of the algorithm, the way that the code is written, the frequency of pixel burning is less because it's now young deciduous forest that already burned. Hasn't yet shifted back to its more highly flammable state. See, what else was I going to say about al fresco? Well, I should say that this actually, the way we, the way the programmers at Snap, Alec and Angie and others worked on these is these are actually averages across 500 runs of al fresco, 100 for each of the different models. So remember I talked about how most of the outputs we're talking about for climate are averages across the 5 best performing global circulation models. But al fresco has to be run on separate models because if you average the models, it tends to damp down the variability, and that completely messes up the calibration of the model, because part of what causes the stochasticity of fire is the fact that you get really hot and really cold months and, that variability. So it has to be run in separate models, but we wanted results from all 5 models so that it would be congruent with everything else we were saying about climate, which is all averages of the 5 models. So we ran 100 runs on each of the 5 models and then averaged across that, so it's a total of 500 model runs that went into this. And this is just essentially the same information, but in tabular form. It's a little easier to digest. Those are the regions on the left, the Kenai River, and so on. So you can see that the current fire return intervals, which are just the inverse of the frequency of burning, obviously, varies from 112 is the shortest there, and 182 is the longest fire return interval. And you see those dropping way down and then actually lengthening a tiny bit again. As I said, things level off in the 2050s and 2060s. So, but you see, for several regions, those fire return intervals going down to around 100 years instead of, 130, 140, 150. So pretty significant change if you think about what the average age of vegetation would be, and you think about the fact that for the first 70 years of a forest stand, you usually have it, starts out as deciduous, and then it's mixed, and it's not considered to be dominated by the conifers until it's about 70 or 80 years old. So if you have, that means there's a really big difference between having a 130-year fire cycle versus a 100-year in terms of how much of the forest is deciduous versus conifer. Because of the first 70 years, so if 130 is your average return interval, it means that particular forest patch spends about half of its lifetime as deciduous and half of its lifetime as conifer. Whereas if it's 100 years, it means it spends 3/4 of its life being deciduous, shifts to conifer, and then burns. And that obviously that has a lot of ramifications for the species level at the ecosystem level. So that's the story being told here.
Nancy, this is Cindy. Can I just ask a question? I'm getting a little lost because you at one point were saying that you guys are averaging across all 5 of the models, but then earlier for the temperatures, you were saying that you guys were only using A2, right?
Oh, I'm sorry. See, that goes back to what I glossed over because I didn't want to bore people with too much of the methods. 2 different things going on here. The A2 is not a model, it's a scenario. So the we use 5 different global circulation models, and we average across all 5 of them. Each of those global circulation models offers, as dictated by the Intergovernmental Panel on Climate Change, all the groups that created those global circulation models were instructed to run their models under different greenhouse gas emission scenarios. So for each of the 5 models, there are these different outputs, like what does your model say the future will look like if everyone burns up all the fossil fuels right away, or if global population increases and then stabilizes, and so on. So you can read little descriptions of what those scenarios, and the ones I referred to are the B2, the A1B, and the A2. Those are scenarios of human behavior, and each of those are fed into the 5 different models. So it's actually multiplicative, just to confuse your life even more. But almost everything I'm presenting here is an output from the 5 global circulation models all averaged together, and it's an output from the A2 emission scenario run. You know, each of those 5 models was run using the A2 emission scenario, and then we averaged all the outputs together. Does that help? It's a lot to try to explain really quickly, and it's all in the methods. It's all explained on the SNAP webpage, but it's really dense.
Well, I mean.
Okay, I was clear as mud there. All right, but I'm going to just quickly go through this. This is management question 23. Asked us about climate and fire. So just a quick rundown. From the literature, we know fire is already increasing in frequency and intensity. And this actually, the question specifically was how is changing climate likely to affect fire? And so this is essentially from the literature, from the fire history, and these are inputs to Fresco. I'm sorry, Scott.
Intensity, you mean severity or intensity?
Actually both, but yeah, thank you for that catch, yeah. And their feedbacks obviously between fire frequency, vegetation shifts, and subsequent fire, as much as possible, those are built into Fresco, and they're new iterations of Fresco are always underway. They're always adding more variables and validating and adding more variables and validating. And as I've said before, changes in fire are likely to have, at least in some regions, greater impacts on ecosystems than direct changes in climate. So that's the comparison I was making between the whole Cliomes discussion, where you have this sort of slow forcing, like, okay, it's getting warmer and maybe a little wetter, and this is like sort of slow push, and then you have fire come in and reset things. And as you were alluding to, okay, what comes back after fire? That's where the two come together, because then the fire comes in, and what comes back after fire may be informed or created by what that push might have been kind of invisible until the fire comes in, and then something really unexpected comes back. So transitions may be abrupt following fire, embedded in there. And then again, based on the literature and on fire modeling, black spruce and deciduous forests may expand, while white spruce are likely to be moisture limited on drier sites. Glenn Judea up at UAF has done a lot of work looking at that, where you get temperature sensitivity on well-drained soils that get drought stressed. As you lose your permafrost, the drainage gets better. So you see some of those shifts. And in tundra systems, more frequent fires are expected, and that's again supported by the literature, but not modeled for this project. And partial replacement of tundra by graminoid-dominated ecosystems is likely. Again, that's Kyle Jolie has been doing a lot of work on the interplay between tundra and fire and caribou as well. So there's new research like that's coming into play, and as much as possible trying to use that to fill the data gaps. So applications, in what way is any of this useful? Lit review suggests that fire has been increasing in tundra systems. Shorter fire cycles in forested areas and fire frequency likely to stabilize over time. Obviously, how that information is useful to a manager depends greatly on what the manager is trying to do, but those are all fairly clear messages coming out of a pretty convoluted set of models. So again, that's kind of take home. Younger forest, different vegetation, maybe some severe shifts after fire, and definitely burning tundra can hammer the lichen, which can have species impacts as well. Then limitation and data gaps. I've touched upon a lot of these already. Fresco is useful at a landscape scale, but as I said before, because you have to average across runs for it to be meaningful, you can't start cherry picking with it. You can't predict fire at particular sites. I mean, you can talk about which sites are more fire prone and use the literature to inform that as well, but you can't make that kind of specific prediction. I said fire severity was not data weren't available for that, and any sort of gridded or consistent manner. I talked about how it was limited to forested areas, and then the feedbacks, again, are tough, because you get a lot of effort into validating the fire model, but how that feeds back to the last section here that I'm going to talk about, the soil thermal dynamics. Again, we know, we have a bunch of answers that are qualitative on this, but there's a data gap in terms of the quantitative analysis. So, got 15 minutes left, I'm doing okay.
Hey, Nancy, can I ask a real quick question before you move on to permafrost? So you have been referring to, the areas with tundra fires versus forested areas, but have you shown us a veg map of what is considered the tundra area for fires in this RIA versus the forested area?
I haven't shown you that, but we can show you that. I don't have that map.
It's going to be in the report then?
Yeah, I think it's in the report. If it isn't in the report, we can put it in the report, because that's...
And that's not the Cliomes then? It's not like, roughly 8 and 12 would be the tundra area? No, totally different. Okay.
Yeah, no, it's part of the inputs to the alfresco model, is basically. And it's a little complicated because, as I described earlier, the alfresco model gets spun up from historical time periods in order to calibrate it, but there is basically, it's not quite the present, it's a few years prior to present, fixed map of the starting point, and that's where we got what is tundra, what is forest, and ultimately, the fully calibrated alfresco model then allows shifts between different tundra types and forest types. So then once you depart from your time present, then everything's all over the place, and you can no longer say what is and isn't because things have shifted. But the way we ran it it was more fixed because we didn't have it calibrated for tundra. But yes, to make a long story short, yes, we can provide you with that map.
And that land cover is not the recommended one, is it?
No, it's a much more simplistic. It's like a yes or no. Forest versus tundra. It's not nearly as fine-tuned and complex as the land cover these days.
But for the purposes of the central Yukon RIA, you guys should have that fully calibrated, so for that,
and that's,
RIA, you're gonna...
For anyone who might have been on the teleconference where we were talking about how we're like way ahead of ourselves for the central Yukon RIA, we're trying to have some really early discussions to talk about how to make these issues of scale play together as well as they possibly can. As alfresco has been improved and more veg layers have been added into that, how to make all that work together. So yeah, long-term vision, but yeah. Okay. I'm going to talk about permafrost, and then hopefully there'll be a few minutes for you to hammer me with questions at the end about permafrost and about how all these pieces play together. So again, this is a briefer segment, and you've seen some of this before. But as I said before, what we're calling a permafrost model is really a soil thermal dynamics model, basically asking the question, what is the, two different outputs. What is the mean annual ground temperature at 1 meter depth, which translates into essentially, is there permafrost at a depth that is ecologically meaningful? I mean, you can have really deep permafrost, but it's not in the rooting depth of any plant, so and it's not in this sort of meaningful drainage depth for hydrologic systems, so it doesn't matter. But at 1 meter depth, that really affects the biome and affects the hydrology. So what is the mean annual ground temperature at 1 meter depth? And this is the output again based on climate modeling and on the Geophysical Institute permafrost model. If anyone's curious about the inputs to the GIFL model, those are all available in detail at their website. Some of those are included in our report, but they use vegetation cover maps, they use soils maps, ground cover to try and get at the different insulating properties and the different like solar reflectance, how much of the heat makes it to the ground and all this. But again, I talked about this quite a bit this morning, but there's a big story here. There's a big shift just by virtue of where this REA is in the state. So I said, with the Cliomes, I said, okay, it happens to be in an area that's oddly convoluted in terms of climate envelope, With permafrost, it happens to be in an area that's sort of oddly clear and full of, full of threshold shifts, from below freezing to above freezing for a lot of area. Everything around the grass is turning from blue to red is a simple way to put it. I do have to add that the caveat, of course, that a lot of this change that happens at a really micro level is not going to be captured, at the level of a couple of kilometers here. But the big story, if what you're concerned about is changing watersheds, then the story really is here. If what you're concerned about is a little iceland on your building site, this might tell you to think about that, but it's not going to tell you whether that iceland is going to thaw this year or next year. And then this is the other output from this model that I alluded to, active layer thickness, obviously related, but the two colors on this map actually are two different variables. For the shades of blue are for areas that do not have permafrost at 1 meter depth. So they actually show the depth of freeze, like how deeply does the ground freeze at the very end of winter when thaw is about to begin, how frozen is the ground. And then the areas that are shades of brown and yellowish show the seasonal depth of thaw, so different variables, meaning that at the very, very end of summer, fall and things start freezing up again, how deeply has the ground thawed? And that, of course, is important information for what species can root there. Is it just the black spruce that can deal with this really, really shallow active layer? Are you going to get into white spruce? Are you going to get in birch and aspen or whatever? So two variables on one map. Again, you can see pretty distinct change over time in depth of active layer. And then this is getting at a different management question, management question 18, which asked effects of changing soil thermodynamics and permafrost thaw in communities. So this just this is showing areas of permafrost retreat. So it focuses more on areas where the active layer is getting a lot deeper, or where permafrost was continuous and may in the future be discontinuous. It focuses less on areas where the permafrost is already discontinuous, and so it overlays it with the community. So fairly simple there, but you can see that change is likely to be more pronounced in the north and the east. So again, you have to take this a little bit with a grain of salt because there are these interactions at the micro level. But applications, which I've been touching on all along, significant thaw across much of the REA. Again, the caveat is that what happens is that the 2-kilometer resolution at 1 meter depth doesn't equate to total permafrost loss, because there's still going to be pockets of frozen ground even in an area that's marked as thawed, and there'll be pockets of thawed ground in areas that are marked as frozen. But it does show a really significant trend on a regional basis. And in terms of the active layer depth, it means that that winter freeze won't go as deep, and it means that in the areas that do still have permafrost at 1 meter depth, that thaw layer will go a little deeper. So limitations and data gaps, again, I've touched on most of these already, so I won't belabor it, but again, the threshold dynamics are key, and the linkages, certainly the literature has quite a bit of information about linkages between fire and permafrost thaw. So what this model that's looking at is modeling what is existing in terms of vegetation layer and soil type. If you throw fire into that on a localized level where the fire takes place, you rapidly accelerate the permafrost thaw because you have black charred ground, and if the intense fire in the insulating layer has been burned off, so you have all this black charred ground absorbing the heat, nothing to insulate it, and you can get much more rapid permafrost thaw, in a burn scar, and then that can really reset what grows back after the fire, because you've got the combination of the burned ground and a suddenly much deeper active layer. So there's some stories like that you can pull out of the literature, but you can't really predict because you can't predict exactly when the fire will happen. But you can still use it to inform management because you can say, yeah, if there's been a fire here, you might see a real threshold shift after it because it's in an area of tenuous permafrost. You had a big burn. It's gonna be different. You know, there's gonna be big change there. So I'm coming in like 4 minutes ahead of my hour and a half of nonstop talking.
Not even a drink of water.
Fairbanks and don't hydrate. Are there any other questions that I can field now? And I know that this is way too much information and way too much of me talking. I know there'll be more questions and, you know, people can dig into the report and fire questions by email.
Nancy, can you explain what a soil thermal regime is again?
It's just a fancy way of saying that, you know, the way that temperature affects and interacts with the soil. So it's the easy way to talk about this section is just to talk about it as permafrost. But because some change doesn't actually have to do with thawing permafrost, but has to do with deeper active layer or soils being warmer or soils being, you know, discontinuous versus continuous permafrost, it's really just awkward terminology saying how warm is the soil and is it frozen.
And how do we know how warm it is? Is that required during a soil survey?
Well, the mean annual ground temperature is ground truth using a whole bunch of cores. So it's a model in the sense of it being a gridded model, and obviously there's not unfortunately a core at every 2 kilometers in a grid around the state, but the model is trying to approximate what the temperature is at 1 meter depth, and then that's validated as much as possible with the test sites.
And how are the test sites in this particular area? Are they pretty consistent across the state, or is this another area where there's a lack of data in this?
No, I'm proud to say there are actually test sites in this REA, but they kind of like just go across. The transect, and again, it's not my research, it's the Geophysical Institute Permafrost Lab, but I've looked at maps of where some of their boreholes are, and they have them going in transect, so they have like a whole line of them going all the way up the Hall Road, you know, like going straight north, like, you know, but they actually have them going westward as well, so they do at least cross this region, and then they go like south down this way. So, yeah, I mean, it's such a big state, and there are only so many people out. There are only so many grad students you can pay really bad wages to go do boreholes for you. Yeah.
I think what Paxton might have been getting at is, and I don't know if Eric Geisler is still on the phone, that we're working with NRCS to do some soil surveys starting next season. So you might be curious whether in the past, it sounds like it was some Geophysical Institute permafrost survey, not NRCS soil surveys, but you got that data from how it would.
I think, and again, I need to check on this. I think they've probably borrowed soil data from wherever they can. I mean, the layers that they use are not like all their veg layers, and they use data from everywhere they can. But there might be, there might be like soil studies that they haven't managed to roll in that they could. So that would be great. If you have info on that, I can try and talk to Sergey about whether that would improve the data set. That'd be great.
Just have one comment about fire. The fact that you identified fire severity as a data gap is severe in the analysis, because the assumption is that the fire perimeters that you see there, that everything is burned, which in fact, most of the time that's not correct. Most of the time, 20, 30, 40% of that may be either unburned or moderately burned. So when you are looking at fire return intervals for those areas, you don't, it skews that, because they may be returning into the areas that have been unburned within the fire perimeter in the first place. And it also has a determination of what regeneration plants return based on fire severity. Usually fire that's not very severe, the plants that are rooted there return immediately, whereas areas that have high severity, actually new plants have to come in and regenerate those sites. So not having that data is critical in going forward with trying to understand what fire actually does.
It's a really big deal, yeah. And you're right to point that out. Although, you know, it's playing devil's advocate, I would say that when you do have, you know, like, yeah, you only have 30 or 40% burn, but that would typically be more of the flammable stuff is gonna go, you know, so if you have mixed forests, yeah, the fire might spare this really old stand of black spruce within the fire perimeter, but more often it's gonna take out the more flammable stuff and leave the younger stuff. So in terms of what Fresco does about, like, resetting the time to next fire, it's not quite as bad as it might be if it were completely random 30%.
It also depends how they determine the perimeter, because when they fly over and do a perimeter, they look at how far these stringers go out, and they may encircle certain, you know, huge areas of unburned area because of the fingers that go out around it. And so, you'd like to say, yeah, it burned the black spruce or it burned these more volatile fuels, but, you know, when they draw the perimeter, you don't know exactly what's included and what's excluded in those.
Yeah.
I've been out there and seen them do this and used some of the products, so,
Yeah.
it's a problem that hopefully will get corrected down the line, but right
Yeah.
now it's,
Yeah, and that's why it's among the data gaps. It is.
I would say we didn't use the fire burn parameters to look at, like, again, and just to kind of quality control what we were using as the burn parameters. If a subsequent land cover map was produced and kind of could outline, it could identify where the burn parameters were. If it identified a lichen vegetation class that we know takes 60 or 100 years to return, and if it was identified on the map, we assume that lichen class did not get burned. So that was one way for us to check based on what the vegetation map kind of said, and checked that with the burn parameters. So that kind of helped us.
unfortunately, the land cover work that was done over the last 15 years didn't always treat that consistently. One image processor would put in the classification for what the return vegetation was. Another one might avoid the burn area completely and try to classify it as what the surrounding terrain was. So that's one area that could have been improved.
And some maps just said it burned. Just left it at that, with no
Right,
information.
or a fire scar, and it was just a fire scar without identified vegetation.